Hi everyone, today we're going to learn about buffer. First, tying to the learning objective from College Board, you may want to pause the video for a minute to read them. So what is a buffer? It is made up of a significant amount of a weak acid and conjugate base, or a weak base with a conjugate acid. A buffer resists change in pH by neutralizing any added strong acid or strong base in small amounts. Now, buffer has a large concentration of the weak acid, HA, and the conjugate base, A-, such as acetic acid paired up with sodium acetate, hydrofluoric acid paired up with sodium fluoride, nitrous acid paired up with potassium nitrite. Because the weak acid ionizes partially, according to the following equation. Therefore, you have a large concentration of the acetic acid molecules unionized. And then if you have the salt in there, it is soluble in water and ionizes completely to form lots of acetate ion. So in the buffer now, you have a mixture of significant amount of the weak acid and the salt, which is the A-. Now the buffer would neutralize any added strong acid or base in small amounts. When small amount of the hydrochloric acid, the hydrogen ion, is added to the buffer, it will be neutralized by the A-, the acetate ion, so the pH decrease will be small. Look at the equation, H+ neutralized by acetate ion to form acetic acid. Now, when small amounts of strong base like sodium hydroxide is added to the buffer, the hydroxide ion is neutralized by the acetic acid and the pH increase is small. So look at the following equation, hydroxide ion and acetic acid to make water and acetate ion. There's a buffer in our blood. Our pH is maintained between 7.36 and 7.42 for the proteins to function. Now, the pH is maintained nearly constant by the presence of buffer. Because in our blood, we have the buffer system of carbonic acid and hydrogen carbonate ion. The carbonic acid would neutralize added base, according to the following equation, to form hydrogen carbonate ion and water. And the hydrogen carbonate ion would neutralize any added strong acid, according to the following equation, to form carbonate ion and water, therefore minimizing the change in pH. Let's try practice problem number 1. I have a buffer containing 50 ml of 0.3 molar acetic acid and 50 ml of 0.3 molar sodium acetate. What is the pH of the buffer system? So first, we write the equation for the ionization of the acetic acid to form acetate ion. This is at equilibrium. Now we're going to calculate the molarity of the acetic acid and the acetate ion in the mixture. And we have 50 milliliter of 0.3 molar over a total volume of 100 ml. So each one is 0.15 molar. Now let the change be the x. So we take away x from the left-hand side and add x to the right-hand side of the arrow. So the new equilibrium concentration for acetic acid is 0.15 minus x for the hydronium ion, and 0.15 plus x for the acetate ion. Now using Kb value, set up the ratio, which is 1.8 times 10 to the minus 5 equal to x times 0.15 plus x over 0.15 minus x, and assuming x is small and negligible. Now solving for the x, which is hydronium ion concentration, which is equal to 1.8 times 10 to the minus 5, which has the pH of 4.74. And therefore, we conclude that when the acetic acid and the acetate ion are of equal concentration, pH of the buffer is just the pKa. Let's take a look at how we derive at the Henderson-Hasselbalch equation. So here is the equilibrium of the ionization of the weak acid to form H+ and A-, and we write K expression equal to product concentration over reactant concentration. Now we rearrange the terms so that we can express hydrogen ion in terms the rest of the species. And then we take the negative log of hydrogen ion because we want to convert it into pH, which is equal to the negative log of Ka minus log of the ratio of Ha over A-. Now we have pH is equal to pKa plus log of A minus over HA. Notice that we changed the sign from negative log of the ratio to positive log of the ratio, and I invert my ratio of A minus over HA now. Now we have the Henderson-Hasselbalch equation, which is very functional to calculate the pH of a buffer system. Choosing a buffer system. Now, looking at the Henderson-Hasselbalch equation, it has two major factors. The first factor being the pKa. Therefore, if we want a pH close to 5, we find a Ka value of 10 to the negative 5. Or if we want to create a buffer of pH of 9, we go to choose a weak acid that has the Ka value close to 10 to the negative 9. The second factor affecting Henderson-Hasselbalch equation is the ratio. We can actually adjust the ratio to obtain small variation in the pH. If we want it to be slightly more acidic with lower pH in the buffer, we add more of the weak acid HA. On the other hand, if we want it to be a little bit more basic with a higher pH, we just add more of the conjugate base of A minus to the buffer. Please note that when we add water, it does not change the ratio because the same volume of water is added to both HA and A minus. The next problem, describe how you prepare a buffer at pH of 9. Now, I would pick ammonia and ammonium chloride because ammonium has a Ka value of 5.6 times 10 to the minus 10. Therefore, its pKa value would be very close to a pH of 9. And I would use 0.1 molar for both because it is easy when I plug them into the ratio to calculate the volume that I need. Okay, so using Henderson-Hasselbalch equation, pH is 9, which is negative log of Ka value plus log of the ratio. Notice how ammonia now is the base, the A minus, and the ammonium ion, which has one more proton than ammonia, now becomes the HA. So solving for the equation and taking anti-log of the ratio, I get 0.16. Now that means I have 16 parts to 100 parts. That means I can mix 16 milliliter of the 0.1 molar ammonia solution to 100 milliliter of 0.1 molar ammonium chloride solution, and the resulting buffer has a pH of 9. So it's relatively easy to do so. Now let's try practice problem number 3. How many grams of sodium lactate should be added to 1 liter 0.2 molar lactic acid to make a buffer with pH 3.5, given Ka is 1.38 times 10 to the minus 4? Now using the Henderson-Hasselbalch equation, we plug in the pH of 3.5, negative log of Ka plus log of the ratio. Since we know that lactic acid is 0.2 molar, we can put it into the ratio, and now we are solving for the concentration of the lactate ion. So using the math, it turns out to be the ratio is 0.44, and cross-multiplying, we get 0.088 mole per liter of the lactate ion. Now, because we have 1 liter solution, and we know the molar mass of sodium lactate is 110 grams per mole, we now obtain 9.68 grams of sodium lactate to be added. That means if we want to make a buffer of pH 3.5, we add 9.68 grams of sodium lactate to a 1 liter solution with the 0.2 molar lactic acid. So summarizing what we've learned today, we've learned the components of a buffer system. We learned how a buffer system resists change in pH when we add small amounts of strong acid or strong base. And that we learned how the buffer functions in our blood system to resist change in pH. We also learned how to derive the Henderson-Hasselbalch equation and the two factors that would affect the pH of a buffer system, mainly pKa and log of the ratio. And then we learned how to choose the proper conjugate acid-base pair to design a buffer of target pH. And we learned how to use quantitative calculation to calculate the ratio so that we can design the buffer solution. If you find that you like the video, please give us a like and subscribe to our channel. And hope to see you again real soon.